Welcome, welcome. Unit 4, Lesson 17. We are looking today mostly at graphing log functions to see what they look like. And it would probably make sense, knowing that logs are the opposite of exponentials, for us to remind ourselves what an exponentially growing graph might look like. We have this value that's going to be increasing and moving upward and upward and upward. Now it can go to the left of the y-axis, but notice that it doesn't cross down below. So that's why in some of our logs we've been getting some undefined values if we are trying to take a log of a negative value. It's because there isn't any exponential down here in the negatives. So we're going to see what a logarithmic function looks like when we graph it. It starts though with a which one doesn't belong, one of my favorite types of warm-ups going on here. And if we think about which one doesn't belong, we could go through all kinds of different ways of what makes each one of these different from others. Looks like that first one is very much where we started our unit, where we have a starting value of 4. This one is a shrinking graph because it's less than 1, and it's raised up to the exponent of x. Now it looks like all of these are actually, I shouldn't say all of them are. Interesting. So this one, what makes it different is that it's back to our most basic format that we have. So this is like back to where we began. It starts at 4. It's a shrinking graph. I can tell because it's less than 1 here with that multiplier. So it's very much like where we started. We're looking at a very basic kind of lesson 1 through 7 type of equation. And what makes G different is that it's the only one that has base E. So I see this is the only one with continuous growth. All right. So this is our only continuous growth graph. It's the only one that uses base E. It still has a starting value of 4. And this one, instead of it being a shrinking graph, that 0.75 up here, remember that that would be losing 25% of its value up here. So I'm going to add that it's losing 25% of its value each time. It keeps 75%, but it's still a shrinking graph. This one is going to be a growing graph. So this one is actually starting at 100% and adding 75. So this one is growing 75% each cycle. Okay, however long a cycle is, however long an x is. So it's a growing graph, so that's something that makes those two different. Let's look at H and see what makes this different. H does not have a starting value of 4. It's our only one that's doing that. Not starting at 4. It starts at 0.75, and this one is growing at 4 times the rate. All right, so each time we go through a cycle, it is multiplying by 4 every single time. So it's growing by 400%. Okay, so it's keeping its 100%, it's adding 300% to it every single time. So we have another growing graph with a factor of 400%. And our final one, our equation here, still has that kind of starting at 4 thing, but this is the only one that's in log form. And this one gets a little bit more challenging to read because our output is of course going to be our exponent. We've got log base 10 of x, and for our different x's we're putting in, we're no longer using x as an exponent, so we're not putting in values in the exponent. Here we're putting in x's for the value, and we're trying to calculate the exponent. So not only is it the only one that's in log form, but this is the only one that's in base 10, because remember there is no base in there So this one would be a multiplier factor of 10. And so we're looking at a base 10, and it's the only one where we don't know the exponent, where x inputs are the value. Not an exponent. So some things that are really making these look very, very different from each other. You've only got one of them that's shrinking, two that are growing, one of them that's in log form. And one of them starts at something other than 4. So some neat things going on. Let's move on to 17.2. We have a colony of 1,000 bacteria doubling in population every hour. I can't help myself. I have to write an equation that goes along with that. Starting bacteria, 2 multiplier happening every hour. So number 1, when we explain why we can write h equals log base 2 of x to represent the number of hours it takes for 1,000 bacteria to reach a population of x thousand, well, it might be helpful to take the equation we've already written here and know that we are trying to get it to equal a population of x thousand. If we have x, this is going to be awkward. It's going to be kind of weird. There is x thousand bacteria. Okay, so that makes sense. If we have 4,000 bacteria, I'd put 4 in for x. I would have 4,000 here. And so we have seen before how we would solve these equations, trying to get that exponent by itself, and our series of steps that we would take to make that happen always started with dividing by our starting number over here. So that 2 base and the exponent h are locked together, but we can move that 1,000 over by opposite operation. Let's divide both by 1,000. And maybe now you're seeing that our thousands would cancel out and would cancel out over here as well. Those thousands would cancel out. We would have 2 to the h equals x. So those lines up here are division. I'm not underlining these words. I'm thinking about using that like to divide to cancel out that 1,000. And then I have an unknown exponent, so if I were to log roll that base 2 to the other side to isolate the exponent, we would have h, the isolated exponent, a log with a base 2 of x. And so we can see that is exactly what they wrote up there. So we can show that division by 1,000 and then rewriting exponential into logarithmic form. When we need to go about completing this table for values of h, that would give us a certain number of thousands. Well, we can start to type this in. We have a base 2, so I'm just going to remind you one more time for each one of these values. If I have something like x thousand, so let's say I have 4,000. If I was thinking log base 2 of 4, there are a couple ways to type that into a calculator. If you have a TI 83 or 84 that has the log base, you could just use the math menu and find a log base. I myself prefer to just remember this because it works every single time. Log 4 divided by log 2. Okay, so I'm just going to keep on doing this same thing. My x values will change in that numerator to each of these x values, but what I find at the equal sign is going to be the h hours. So let's turn on our calculator and let's get ourselves going on this. I would have a log 4 close parentheses divided by log 2, enter. Alright, so that makes sense. 2 to the second power equals 4. So that's when I'm looking for 4,000. So keep that in mind also too, that some of these might be faster just in our head, that 2 to what power equals 2 is going to be the first power. 2 to what power equals 1? That's of course going to be the 0 power. 2 to what power equals 8? Well, 2 times 2 is 4 times another 2 is 8, so I needed 3 of those to get there. So the fourth would be 16. It's when I start getting up to 50 that I'm going to turn to my calculator again. So I would be doing log of 50 divided by log base 2. Sorry, typing that in my calculator here. Ooh, I need to go back and check my other values over here. Am I getting that right? I'm not closing my parentheses. See, even teachers make mistakes. So sorry about that. I forgot to close my parentheses. So log 50, at least I knew that there was something wrong there. So I'm even going to leave that mistake in my video because it's good to show mistakes sometimes. So I needed that log 50 divided by log 2. Make sure you close those parentheses. We should be getting about 5.644, rounding to 3 decimal places. And I need one more calculation. Log of 80, close parentheses, divided by log of 2. And we see that this is like 6.322. All right, so we had bases raised up to different exponents that would get us a certain population of bacteria that's going on here. And it asks us next to plot those pairs on the coordinate grid. Inputs down here are our x's, so our x of 1 is going to just be an itty bitty number over here, and it's at 0. Slide that up so you can see it better. At 2, our value is 1. So 1, 2, 3, 4, 5. Good. All right, each of those is 1. For 4,000 to 4,000 bacteria here, we're up at the whole number 2. And our x is 8. That would be this tick mark right here. Our exponent was 3. 16, so 10, 12, 14, 16. Our exponent's up at 4. Our x of 50 was at about 5.644, so I'm going to just follow that over at 50. And last but not least, all the way over at the end here, 80, we need 6.3, so that's just above that next line. To make 2 observations about the graph, well, we can kind of connect it, and it's got this kind of curve going on. Okay, so I can kind of start connecting those dots, try to do it a little bit better than I did. I don't know. And if we're making 2 observations, maybe you're observing that it doesn't go through the origin. It doesn't go through 0, 0. And it is growing quickly at first, but then it kind of tapers off. Right? That curve kind of flattens out. You may have heard that statement a little while ago. And so we can make a couple of those observations. Whatever observations you'd like to make, certainly make those observations, that it changes very quickly at the beginning, but then it just kind of starts to taper off and go very horizontal. You might be making the observation that this is very closely related. In fact, it's an inverse of our exponential function. So an exponential function starts off growing slowly and then starts growing faster and faster. This one starts growing faster at the beginning and then starts growing more slowly as we go. So it's an inverse of our exponential function, which means it should be able to cross over our x-axis into some negative hours, but we know in reality that is like time travel. But it could be prior to when it started the count. So before they counted these bacteria, maybe it was already there. We can also type this into our calculator, of course. I always want to think about how we would enter this on a graphing calculator if you have one, or on a Desmos. We've got this idea about going to our y equals right here on the graphing calculator. And I am going to use, in this weird time, that log base option. And we have log 2 of our variable x right here. You could also still type this in as log x, close parentheses, not raised to, no, not raised to, divided by log base 2. These should give me the exact same graph. So I'm going to zoom 6 so I can see a 10 by 10. And there's that curvy graph that we're seeing. And in fact, it does go below the x-axis. So nice to see that. Use the graph to estimate some missing values in the table. We could use our graph. We could also use our calculator now that we're pretty smart about that. But if I want 10,000 bacteria, I'm going to go back to my graph. I'm going to find the thousands here. And what this is telling me that if I have a known population of 10,000, I'm going to follow it up, then follow it over. And it should be somewhere around about maybe 3.5-ish, right? Of course, some of this is going to depend on the graph. We know it's definitely going to be somewhere in between 8 and 16. So 10 is between 8 and 16 for our population. So it's going to have to be between 3 and 4. So maybe like 3.4-ish, because it looks like it's probably a little closer to 8 than it is to 16. I'm going to guess. So a good estimate, about 3.4. And for a population of 24,000, go back to my graph. I'll do this one in orange this time. 24,000 is here. Follow it up. Follow it over. We're probably at about 4.5-ish, somewhere in there. Definitely between 4 and this 5.6 that we're seeing. Oh gosh, you can't see any of that. Sorry about that. So I followed that 24, followed it up, hit the graph, followed it over, and found it's about 4.5-ish. That's a pretty good estimate. Let's put that here. And 72 would be right about here. Follow it up till you hit the graph. Follow it to the left so you can figure out what its value is. It's just above 6. But below 6.3, because 80 already told me 6.3. So I'm going to guess 6.1. I could also go to my calculator and see, remember if we're thinking about knowing our x value, log base 2 of a known x value, I could actually calculate this thing like using log 24, log base 2 of 24. Log 24 divided by log base 2. Ooh, we said 4.5 and it's actually 4.6-ish, so I got pretty close. So that's pretty awesome. So tables of values can also help us, graphs can help us, and calculators can help us get exact values. 7.3, move along with me. Earlier, we saw that h log base 2 of x represents the number of hours for 1,000 bacteria, doubling every hour to reach a population of x in thousands. Okay, suppose the function d, defined by log base 10 of x, represents the number of days it takes 1,000 of another species of bacteria to reach a population of x in thousands. How is this population of bacteria growing? Well, what we're seeing is that our one earlier had a base 2 and it was doubling every hour. So I'm going to make that connection up here in our example before. And this one, the only change is that this is in base 10. So if we want to describe how is this population of bacteria growing, it looks like it's getting 10 times larger every hour. 10 times larger every hour. So this one with this base is growing much, much faster than just doubling. This one is getting 10 times larger every hour. It asked us now to graph D using graphing technology and make 2 observations. If you are at home without a graphing calculator, go to desmos.com. If you are here with a graphing calculator, let's graph those 2 in there. I'm going to actually leave in my graphing calculator here. Actually, you know what? I think I might go to use a Desmos. Yeah, I think I'm going to go use my Desmos. So bear with me. I'm going to launch on my computer screen a Desmos screen. Alright, so we're going to desmos.com. I'm going to use my graphing calculator here. Let me just turn this into display mode. I'm also going to shift my graph down so I can see, kind of like the same one that we saw in our workbook, that it's going from 0 to 10 on my Y scale, but my X scale went all the way up to 80. Alright, so I'm going to go over to my little wrench up in the top corner and change my X scale to go from where I have it right now all the way up to 100. Okay. This is just going to help me see better something kind of like what is on our paper before. So the first one I'm going to graph is the log base 2 of X. That little keyboard, does it have it? Oh yeah, let's go to functions. Scroll down. I think they're going to have a log one for us. There it is. Log of X, but I need base 2. So I'm going to have to type in, I guess I'm going to have to close parentheses and then divide that by log of base 2. Okay, so I've got log of X divided by log 2. There's our first one that we graphed on section 17.3. And to graph our new one, I just need that exact same thing, so I'm just going to copy my equation up above, and this one is in base 10, so I'm going to divide by log 10. Check that out. So a larger base has a shorter graph. That's pretty interesting. And I see that makes sense though, because if I were to think about exponential functions, if it was exponentially growing by 10, so 10 raised up to the x power is growing so much faster. It's this green one here that just came in. It's growing faster than 2 raised to the x power. There we go. So since our green one is growing faster, when we do the inverse of it, it's going to plateau at a lower, that's going to plateau faster as well. Okay, so the ones that grow faster are also going to plateau faster in a logarithmic graph. Let's sketch and jot some notes on some of this in our workbook. Oh, I'm like changing my, sorry. I'm pushing buttons on my rocket cart and I don't need projectors on anymore. So graphing our technology of what we had from 0 to about 10 up here and 0 to about 100 over here. Log base 2 looked something like this. And our new graph, base 10, is actually much, much shorter, something like this. So it still has that curve to it. It's still going to taper off into a plateau faster. So I'm going to get this idea. Two things that I'm observing is that it's a much shorter graph. And it changes extremely rapidly at first. And then plateaus. Using our graph to estimate some of these values, d of 50, that means that we want to know here, I'm going to interpret this input output, d of 50 is telling us that the population is 50,000. And our output is going to tell us how many hours it takes to get to a population of 50,000. I'm going to flip back over to my Desmos. I'm looking at just the blue graph, so to keep myself in check, I'm just going to turn all the other ones off. And if I want to find at 50, that'd be right about here on my graph. And actually Desmos will tell me exactly at 50, because I can drag my dot to be right at 50. Well, it was right there, 1.699, so about 1.7. Okay, so that took about 1.7, and remember that output is the hours it takes to grow to that population. It also asks us d of 20,000, so we're going to have to adjust our graphing window as needed, at least that's what our workbook says. So if I need an input of 20,000, my x needs to go up above 20,000. I'm going to put that at 25,000 on my Desmos, 20,000 now on my screen. About 4.31 is what it's telling me on my screen. So on a population d of 20,000, I already forgot my number. I said about 4.3. So the population of this bacteria is not just 20,000 bacteria. We would just put a 20 in for x if we wanted that, right? This is 50 with a population of 50,000. This is 20,000 thousands, so we're actually talking about 20 million bacteria happening at 4.3 hours. So comparing this 50 to the 50 that we saw before might be pretty interesting to look at. Here when we have a base of 10, it only takes 1.7 hours to get to a population of 50,000. On the other side over here, it took 5.6 hours to get there. So it took much, much longer here. Remember, this is where it was base 2, so it was doubling every hour. So this took 5.6 hours to get to 50,000. This is 10 times every hour, so it takes much less time to get to 50,000. And then I need to estimate or find the population after 5 days. Okay, a couple things we got to convert first. Everything we've been looking at is the number of hours that we're giving it to grow. So 5 days So I need to do 24 times 5 to figure out how many hours we're talking about. 5 times 20 is 100, 5 times 4 is 20, so this is 120 hours. So we are looking at when does log base 10 of x, that's going to give us the population, equal 120 hours of time. Well, this looks like we want to be back in exponential form because we have a base 10 raised up to the 120 known exponent going on here. This is going to be a huge number. I can tell it's going to be a huge number because it's a 1 with 120 zeros. Okay, so I'm not really going to write out all of these, okay? We're going way, way, way out there. 120 zeros. That's a huge, huge number. So 5 days, if we're letting it grow that much, we'll be way over the 20 million population that it took only 4.5 hours to get to. Giving it 5 full days of time is just a gigantic number. Absolutely massive. If you type it in your calculator, you're probably going to get one of those E things like times 10 to the somethingth, right? So it's going to give you an overflow, exceeds the range that it can display. What is this one going to tell us? I'm so curious now. I love math. Turn on, calculator. 10 raised to the 120th power. Oh, it's going to give us an overflow error too. So that just tells us it's a gigantic number. Huge. All right. We have a little, are you ready for more? How do they compare? And it asks us to graph them both on the same axes. Spoiler alert, we already did that right over here. So making some good comparisons going on. Now that's going to be helpful as you look at some of your practice problems. I think they ask you where these ones are going to meet, and which they have some unlabeled ones. They're going to ask you which base. So our cool down and our summary here are some great ones to use that comparison. Log base 2 versus log base 10. There we go. Lesson 17. Thanks, guys. Appreciate you watching.